I will answer group by group. In other words, if you have questions about this group, then ask me. If you don't, then I will go to the next portion. So portion by portion approach is better than just the whole thing together. First of all, we should label those. Then what does this mean? For instance, what does 3 mean? Or vertex of 3 mean? It means specific position. For instance, this means 3 over 5, or generally m, right? 3 means 3 over m, and then 1 over n. So this is the meaning of vertex 3. So in other words, once we have the index, we know the exact location. So these numbers mean the location. And with these things, we want to create the linked list. In other words, vertex 1 is linked to this one, right? So we want to find the connected links. By our design, we have east side link, northeast side link, north side link, west, southwest link, and south. So we have 6 links, right? But because of our design, if we design differently, we may have more or less linked nodes, but we want to have this. So we want to store this kind of info. So link information of 3 consists of 6 node indices, right? So these kind of numbers should come here. So with 3, east side has 4, right? East side has 4, and this side has 8, and this side has 7, and this side has 2, and then this side has 11, and then this side has 12. Of course, as I mentioned before, this isn't the only approach. You may develop different approach if you want, but my approach depends on vertex and link information. Vertex and link information is important, especially when we integrate or when we find the basis function. Afterwards, after having this, we will use vertex information and link information from 1 through the 28th node, right? We have total 28 points. And for technical reason, we will use 0 if nothing is there, right? So this number can be replaced by 0 if nothing is there in the direction. In other words, northeast may not exist if it's the right-hand side boundary. Right? If it's the right side boundary, then east or northeast doesn't exist. And we technically use 0. So this way, we completely design the background, and afterwards, what we do is this one. We traverse every node using link information, right? Linked information. So we, first of all, we check the first node, and then with the first node, we traverse all the surrounding neighbor nodes, and then you, for instance, do integration or find the height for the basis function. So to do it, what we do is this one. We initially run something for triangle. So triangle number 1 through possible triangle number 6, right? So this side triangle is the first triangle, right? And this side is the second triangle, and so on, right? So we run these things, and then for technical reason, we use this kind of idea. Point 1 is the center plus northeast, east side, right? This is point 1. Technical reason, we always start at the horizontal position, right? So this is the center. From the center, we pick the first point, right? This is P1, and so on, right? And then P2, P3, P6 is defined. P6 is center minus south. And then for another technical reason, we define P7 equal to P1. So we create a cycle for technical or for convenience. After doing this, all we need to do is just making a loop. Big loop runs from first node through the final node, right? 24th, right? First node, second node, and so on. And for each node, we traverse 6 nodes, right? 6 linked nodes. That's the way. So essentially, this is what we did. And technically, how do we do integration? So it solves both cases. First of all, how do we find the height? This is the first part. And the second part is, how do we integrate? So there are 2 things we need to consider. Why? Because height is questioned on homework 8, and integration is asked on the final. So we do two things separately. First of all, to find the height, we check whether random points given by the user, for instance x, y, is inside this triangle or not. Right? So first of all, this is the domain, and this is the center that user may pick, right? This might be the center that user chose. Then we check these 6 triangles, right? We check these 6 triangles, and then xy point is given by the user. Then we should check whether this xy is inside some of this triangle or not. If it is inside, then we calculate height. If it is not inside, then it is 0 by definition. So I read some homework return, and I found that some people didn't make it robust enough. So their case works for under some condition. But generally, your Pij xy could be anything. This ij could be anything between 0 and 10, right? J could be between 0 and 10. So ij could be any number, 0 to 10, 0 to 10. xy could be any number inside the domain. For instance, 0 to 1, 0 to 1. Any number, for instance, 1 over square root of 2, 1 over pi. Any number can be plugged in this position. Then your function, your implementation should track down necessary part. First of all, ij determines center, right? I and j determines the center. If it is 0, 0, is this place. If it is like 5, 5, then it would be 0.5, 0.5. So your ij determines the center, and your xy could be inside this neighborhood, or it might be outside. So you should determine this. Then how can you do it? It all depends on one simple function called inside the triangle, right? Inside the triangle, and it consists of point and then triangle information. So point, to represent the point in a plane, we should use 2 numbers. To represent a triangle, each vertex should be given, right? Each vertex should be given. Then for this vertex, 2 numbers. For this vertex, 2 numbers. So total 6 numbers. So total 8 numbers are plugged in. Then you should implement this algorithm, right? Your algorithm determines whether this point is inside this triangle or not. Of course, I completely explained this before. So you should check whether this happens or not. And then we run for these 6 different triangles, right? So we check this for the first triangle. And if it fails, we check this for the second triangle, and then we go on and on up to 6 triangles. How? We make triangle by using these things. How? Let's do it. We run, for instance, index from 1 through 6, and then first triangle is created this way. First, so let's use W. W1 is the first index, then it is the center, right? Center position becomes the first triangle, and in technical MATLAB style programming, it means this. First one and then this one, right? So this is center. Of course, center, I mentioned, right? Center is like 0.5 that we can create, right? Vertex information. So center is now determined. So always, first vertex is this center, right? And then second vertex is pi. I vary from this east side point to the east side point in the end, right? So I in fact vary from east side to south side. And finally, we need 3 points to form a triangle. And third triangle is pi plus 1, right? Of course, this is not actual programming, but just giving you the idea. So any questions about this design? So we are checking each triangle. How do we form each triangle? We always choose the first vertex using the center. Center is determined by ij plugged in by the user. So ij is plugged in by the user, and this determines the center, right? This determines the center. The center is always first vertex. And then these surroundings are very easily determined, especially when you use ij. You don't even have to worry about linked list because east point is like 1 over n advanced, right? Advanced in the x direction, right? East side. Or northeast is 1 over m advanced, and then 1 over n advanced in the y direction. So things like these will determine the position. So we do these things, and then for each triangle we check, and then after forming a triangle, we use this W information, right, in this position, and then XY information in this position to check whether your point is inside the specific triangle or not. So if it's inside the specific triangle, then you do something. If it's not, then you just continue through all these 6 triangles, and then whenever some kind of hit happens, you return the non-trivial result, but nothing happens for this 6 triangle, you return the trivial result, in this case 0. That's it. So this is the homework A part, and if you have any questions about this design, ask me. So in this sense, program isn't very big because you don't even need linked list here in ij case, right? In this case, just simple design of ij and then northeast, east, things like this, right? East side point, and then south. I explained these things before. If I write it one more time, roughly, center looks like this. Center, if you use MATLAB, it is this like this, right? If you use Maple, you may use I over M and J over N, right? So center looks like this. And then east side is nothing but 1 over M and then 0, right? And then northeast is 1 over M, 1 over N. These kind of things determine these 6 points. So in this sense, you don't even need link information for homework A. Just this thing will do. Then you may have different method for homework 8, but using this idea might be better because in the future, not necessarily in this course, but in the future, you need to program something, and you may encounter a shape like this, right? And then you may have vertices not in uniform pattern, right? Then you should find each triangle separately instead of using just one triangle and then shift. So instead of just forming one triangle and then shift it for every case, it might be better to really form actual triangle and then calculate the basis values. So this is homework A. If you have any questions about homework A part, ask me. Homework A part is trivial in this sense, right? Essentially, creation of inside the triangle checking and then neighborhood checking, right? There are 6 possible triangles, neighborhood checking. It's not here, but neighborhood checking is here, right? And inside neighborhood checking, and then we form each triangle to send the information. So this part was completely explained before, and then it is reviewed today. But if you still have a question about homework 8, ask. Then the next thing is the tougher part, FEM. FEM requires these things, A, J, K, or Kj, defined by the whole region, right? Whole region of delta, gradient, dot product gradient, dot product dA. So this thing should be done, but we want to break this up into small integral, integrating over first triangle and second triangle and then the last triangle, right? So we are integrating over small triangles, but many of these values are zero. Only neighborhood values have non-zero. It's like this. If we consider the analog in one dimension, we had basis functions like this. Assume that we are multiplying basis functions like these, then this 0 will suppress any value here, right? And then this 0 will suppress any value here, and then if we multiply these two, f, g multiply together, then it will become flat. The only chance that we have some non-zero value is having the same fg, then we may multiply these values together to get non-zero value. Or one off. This could be f, and then this could be g, right? So either this case or this case, we may have non-zero value. Other than these cases, we have 0. Very similarly, even when we apply these things to the two-dimensional domain or even three-dimensional domain, if the center of the first if the center of the first delta, del phi sub k, and center of the other one are linked together, if they are not linked together, then, as I showed you, the product will become eventually 0. Product will become eventually 0 because of this effect, right? If two centers are not close enough, then this kind of dot product value will become 0. So the only chance that this survives, or this integral is non-trivial, is the case when two centers are either the same or one off, right? One off is vague. It is clear in one-dimensional case, but in two-dimensional, one off is a little bit meaningless, so I use the link. If two nodes are linked, then we may have non-zero integral, but if two nodes are not linked, then we have no chance. In other words, assume that we have phi k with gradient value centered at this point, and then assume that we have phi of j centered at this point. Then what happens? Because it has height 1, right? It has height 1 here and height 0 here. Similarly, it has height 1 and height 0 here. So what happens is the same. This 0 will suppress all the meaningful values on the other side. In the other case is this. If because of this will suppress any value here. That means eventually if we consider dot product, all the values will become 0. The 0 here, for instance, outside this neighborhood, we have 0, right? You have 0, right? You have 0. Do you follow me? Outside this neighborhood, 0. Then 0 is multiplied to anything here. No matter what is here, 0 is multiplied, then this will become 0. Similarly, if we center at this point and then consider the surrounding, all others will become 0. Because of this reason, Only when j, k nodes are close enough, we consider. Close enough is linked, right? Means linked. When they are linked, we consider. When they are not linked, then 0. Integral is 0. So in this sense, theoretically, it should be very complicated. Theoretically, right? It should be very complicated, or it should be very tedious, because there could be like 200 different triangles. But we don't go through all the 200 triangles. In essence, we only go through 6 triangles, right? Right? We only go through integral over 6 triangles, right? Integral over 6 triangles, 6 surrounding triangles with pivot, right? Like k or j can be used as pivot, right? So we determine the pivot, and then we consider 6 triangles. Any questions up to this point? Because of this reason, now we are ready. So we need to solve the differential equation, and then because of this derivation, long derivation, we now arrive at this simple fact. And then eventually we will get this system, right? This system. So the goal is solving this system for C, because C is the coefficient that we can use to assemble the solution, right? To assemble the solution, use C. Basis function is already created. Then using this C, we assemble the solution. So our task is the determination of CK. But I want to mention this thing because there were some questions. Why did I ask homework 8 and final separately? Homework 8 has nothing to do with differential equation. Homework 8 is just creation of basis functions, no matter what differential equation is given. Or even without any differential equation, we can do homework 8. Do you follow me? Homework 8 is just determining basis functions. No matter what, we just break up, then we can create basis functions. This final exam has these things. Final exam has these kind of things, right? Has this kind of differential equation, and then solving this differential equation using Galerkin approximation and so on. So this is homework 8, and then now, final exam, and then, as you can see, we should solve this kind of system. So homework 8, final exam requires the calculation of these things. To find this C, we need to find all this A, right? And then B coefficient, right? The entries. A matrix entry and B matrix entry. And how many numbers are involved here? For these things, 1 to L, L is the interior number. For instance, if we break up the interval by 10 subintervals and 10 subintervals, then interior points is 9 times 9, 81, right? So we should consider these things for 89 numbers. 81 numbers. 81 numbers. And then 81 numbers for K value, and then for J value, right? And so on. Total 81 numbers. But as you can see, it's double array. So 81 multiplied by 81 numbers. So very many numbers, right? About 6,000. So you should not be confused between the basis function part and the FEM part. They are separate. Of course, we use the same cycle, same program idea using cycling. And then now, how to calculate this thing? How to calculate this thing? A is almost explained. As I mentioned before, once we say A and then J, K, then for instance we use this as pivot. So we now have J, K, J, K. J is already determined, right? J could be like first, second, third, and ninth, and then 11th. First, J could be 11th node, right? It could be 11th node. J could be 11th node. That means in our design, first one is here, 9th one is here, and then 10th, 11th, about position. 11th node means actual position is 0.2 node, right? 11th position is 0.2 node. Then at this point, we can search for the linked list, linked nodes, right? So it is 11th node, then 12th node is linked, and then 20th node is linked, and then 21st node is linked, 10th node is linked, and 82nd node is linked, 80, the left side is first node, right? First and second, right? So these are the linked nodes. So we should check whether our linked list of this J's node, right? So linked list of J's node, that is 11th node, has this K value. But as I did, this linked list should have these values. And then whether K belongs to one of these things or not, we should check. If K is inside this number, then they are somehow related. They don't vanish, right? The product do not necessarily vanish, right? Product does not necessarily vanish if this K is inside this number. But if K is not inside this number, then they are far apart. Then we can easily return 0, right? So if it is in, then do some calculation, right? Do some calculation. If C is not inside this thing, then return 0 as your integral, right? So your integration becomes 0. That means your A, J, K is 0, right? So it depends on KJ combination. If KJ are close enough in abstract impression, in actual impression, if K's linked list has the J value, or J's linked list has K value, then we can return after doing some value, after doing some calculation. But if they are not close enough, then you should return 0. So in this sense, if we really run, our matrix A has a lot of 0 values. Why? Assume that our J represents some node here, like 11th node, right? Our J is 11, and then K is like 81. So J is 11, K is 81, then there is no chance to have any common value. So because of this, we should return 0. So 11th node and first node might be linked, right? And so on. So there are maximum 6 possible cases. So even though superficially this integral looks bad, we don't have to go through all these 200 triangles. We don't have to go through all these 200 triangles, but we just integrate over 6 linked triangles. So I have been a little bit abstract up to this point, but if you have any questions about this abstract or theoretical part, ask me. If you don't, then I will finalize and then review the necessary stuff. Questions? So after this, we can really design. Almost the same design as the previous one. So take a look. What is given? We should always check what the given things are. We have A, K, J means we have, I'm using K and J doesn't matter, right? A, J, K, or K, J, doesn't matter. These two numbers are given. Then K determines what? K determines vertex position, right? It determines vertex position, for instance, point to point 2, right? This K is given, then this K determines vertex position of the point. And it also gives the link information. It gives the link information like I did, right? It is like 12 and so, right? Link information. So once K and J are plugged in, automatically we know these things. Then using these things, we can do the integral. How? Almost the same as before. So let's go to the next page. So K is given, and then J could be something plugged in, right? Then vertex 11 is point to theoretically, and then link information of 11th is like 12th, and then 21st, and then 20th, and then 10th, and so, right? And then first and second, right? This is the linked information. With these things, we can completely integrate it. How? We run these things from the first triangle to the sixth triangle, right? We have possible six triangles, first triangle, second triangle, and so on, possible six triangles. To run it, we do the same thing. First position is the center is always vertex, right? Center is always the vertex K, right? And then position 1 is this vertex 12 is the position 1, right? Or more technically, vertex linked list of 11 of 1. Do you follow me? A little bit abstract, but this is it, right? So first position is vertex 12 position, east side, but that is nothing but vertex linked list of 11 had 1 here, right? 11 had 1. So this is the vertex. If you don't understand, ask me. So this is P1, and similarly, we can do these things for. So here, I don't even arrive at triangle consideration. I only arrive at the determination of surrounding points, right? So point index 1 through 6, right? Point index is being determined. Point index is being determined this way. So we can change this to point index instead of using specific number, point index, right? Point index. So then this disappears. If you don't follow me, ask me. So point index is determined. First point, second point, third point. So we determine all 6 points. After doing this, we technically add 0.7. 0.7 is 0.1. So we completely determine the points. Why do we need this step? Because when you use index of vertices, we do not know the actual position. So this determines the actual position. All surrounding 6 points are determined by this routine. In other words, we are ready to make triangles. Then after this, we really make triangles. So now, after this, triangle number 1 through 6, right? Triangle number 1 through 6. How? Vertex 1 is nothing but the center. Right? Center is determined from the J index or K index. I cannot remember it. Right, K index, right? Center is determined from this, right? I should have used. So center is determined by this line, right? Always, first vertex is determined this way, and second vertex is easily determined. Vertex, this, instead of using triangle, I will use index. So I will use index I, right? I. Second vertex is nothing but pi. And the third index is one advanced point, right? Third index is pi plus 1. Then we can form the first triangle when I is equal to 1. When I is equal to 2, we can form the second triangle. When I is equal to 3, we can form the third triangle. So we form 6 triangles this way. But initially, when I is equal to 1, it's first triangle. For this first triangle, what we do is this one. We do the integral. So for this, so let's say for I's triangle, we integrate. Any questions up to this point? Then assume that if this J is exactly the same as K, if J is exactly the same as K, then what formula should we use? If J is exactly the same as K, then we should use this formula. Right? We should use this formula. Because I always use first index using 1, right? We're using index 1. The first vertex using index 1, right? Index 1. So we should use this formula if K and J are the same. If you don't understand, ask me. Yes?
So we use that formula for each one of the up to 6 triangles.
Right. For each, we are not caring about everything together. We are just considering one triangle at this time.
Right, but then the sum of all of it
Right.
goes in one
Right.
index in the AKJ matrix.
It is right. It is right. And for fixed K, we run it from 1 through 6, and then we may get some non-zero value here and non-zero value here, right? And then this kind of sum is going into AKJ as you mentioned. So we run through first triangle and then some triangle and then sixth triangle, right? So we run through these things from the first through sixth triangle. And then if we have non-zero value, we add these non-zero values to store in AKJ, as you questioned. But let's not worry, at this point, let's not worry about this AKJ determination. Let's worry about just the integral at one triangle, I's triangle integral. So take a look. This is the situation. K is fixed, like 11th. J might be random. J could be 1, J could be 2, J could be 3, J could be 81. We don't know. So it's time to check J value. If J is this value, 11, so now instead of using this question mark, now if J is 11, right, J is 11, then use first formula. Right? If J is 11, right? J is randomly chosen K. J and K vary from 1 through 81. So J could be 11, K could be 81, and any combination. So we initially pivot with just the given number, J, 11. Now we check 6 possible triangles, and then now we check whether this K is inside these 6 triangles or not. And if it happened to be the center position like K itself, then we use this formula. We use this formula, right? So we return. So by using this formula, we return the first integral, right? As the value of this integral, right? Value of this integral. We are integrating for each small triangle. If you have a question up to this point, ask me.
First integral means first of the 6 possible 6.
Right. There we are traversing these 6 triangles one at a time. Then this is done. But it may not be even close. So this is the first if case, right? First if case. Second if case. If J is in the linked list of K. Do you follow me? If J number is in the linked list, like 12 or 20, 120 or 1 or 2. So if J happen to be inside this linked list, then they are not the same because we already checked the first step, but they are in the linked, so they are one off, right? They are one off, meaning we should use what formula? One off, second formula. So we should create a routine doing this. So if this happens by using second formula, right? Second formula, return second integral, right? Second integral means the integral that appears here. First integral and then second integral. Any questions? And if even this fails, then J and K are far apart. Written 0 as the integral of the triangle. It's not the integral of the whole thing, but we are doing integral by integral, triangle by triangle. So first triangle is done, second triangle. So we are doing these things for 6 triangles. Then after doing these things, we collect the value of each triangle. So value is different from vertex, so I will use value of 6 triangles are defined, right? So value of first triangle is the integral of the integral result, right? And the value of the second integral is the integral result, and then value of the 6th triangle were all returned, right? So inside this you can form value of ith integral, right? Base value of ith integral is returned in VAR, right? VAR. So we run for each triangle and then we accumulate value 1 through value 6. If it's not a triangle, then it is 0, right? If it's a triangle, especially linked, then it returns some meaningful value. And then finally, after finishing this loop, we return sum of the values, right? Sum of the values, right? Sum of the values as the result, and then this becomes A, K, J. So if you have questions, so I completely explained these things today, and of course last time I even showed you the actual programs, but please browse these things and ask. Yes?
So none of the values in the link list are 0 for any of the interior nodes, correct?
If J are related, it is not just K acting alone. K itself has surrounding numbers. But we should compare the relation between K and J. If J happen to be inside this, then something may happen, but J does not happen to be.
Yeah.
But
so the AKJ matrix is only related to the interior nodes, not the boundary conditions. We're only summing from 1 to L, right?
right, essentially right.
So every node in the AKJ matrix will have all 6 triangles.
Right.
Right? Yeah. Only the B matrix deals with the boundary.
Right. But for technical reason, we don't want to make 2 different programs to calculate A from 1 to 81 and then 82 to 121. We want to make it all together. So technically, we overcome it by using zero linked list, right? In the link information, you can use zero index. Then zero index means there is nothing. Then that way, we can combine all these things together. But right now, as you mentioned, in interior points, always we have 6 surrounding points, right? Everywhere you have 6 triangle surrounding. But this is a little bit vague. Even this is a little bit vague. I said this, right? I said this. But this is for abstract purpose. In real programming, you should do what? This. Once we determine one triangle, right? Once we determine i's triangle, this is the situation. Once we determine i's triangle, this is the situation. So we don't know the actual points, so we already say, oh, this is center, right? So vertex 1, right? And then vertex 2, and then vertex 3. Right? This is the situation. And to determine these things, I used center, and I used pi, and I used pi plus 1. Do you follow me? Then this means so I'm making it programmable, because this is not programmable, this kind of thing. But I'm making it programmable. How did I determine pi in the first place? Do you remember? How did I determine pi? How did I determine pi? Using linked list, right? Using linked list I determined. So i's position determines pi position. So the hint is here. In other words, to determine this thing, we use linked, right? Linked, I intentionally use 11 because if I use too many indices, then you may be confused. I use 11. 11 has linked list, right? So 11 has linked list, right? Among these linked, there are 6 values, right? So among these things, I'm using I, right? This is the index, actual index, involved index. There are 81 indices, interior indices, right? So among these 81 indices, I pick the index related to this point. Similarly, I pick index related to this one. In other words, if k happened to be this index, or if k happened to be this index, then it means this. It means this statement. So always when you program, abstract thing should be converted to actual comparable thing, right? So if you don't follow me, ask me. So this way we check whether 2 triangles are connected or not. I mean, it's a little bit less abstract, right? 2 nodes are connected by 1 line or not. So this is the checking part. So this part is a little bit abstract, but now it is very precise. So if they are linked this way. So essentially we are done. Take a look. J and K are random. I pick 11th J and then 81st J. K. I mean, K is 11, J is 81. I chose this kind of numbers. Then for this number, I created 6 triangles, and then I go through these triangles and check whether this node number had 82 or 81 or not. If it doesn't, then there is no chance of having non-zero number. So all the universe will become 0. Because of this reason. Because of this reason, right? Because of this reason. But if they are the same, J and K happen to be the same, like 11, 11, then as you can see, we use the first integral formula to do it. And then finally, if it is the second triangle, then as you can see, it is a little bit technical because we are doing these things for the first and second triangle, right? So assume that this happens at this second node. Assume that this happens at the second node, then what should we do? We just leave this order alone, right? Leave this order alone. But assume that this happens, then we switch this. Because our formula is developed for first and then second one, right? First and second. So this is the idea. So roughly, I completely explained all the necessary things. If you don't understand what I mean, you can ask me, then I will completely explain. Yes?
Could you maybe make a small example and fill out the first one or two entries of the AKJ matrix?
No problem. No problem. So we break this up by 5 subuniverse, and then about 3 subuniverse in the other direction. And then we choose interior position like this so that we don't touch the boundary. Then first, second, third, fourth, fifth, sixth, seventh, 8th, 9th, 10th, 11th, 12th, and then 13, 14, 15, 16, 17. There are 30 different nodes, right? Total 12 interior nodes, and then 18 boundary nodes. Then, let's pick 6, right? Assume that K happened to be 6. We are calculating AKJ, right? K happened to be 6. And then J, if J is too far away, it's very uninteresting. If K is like 12, then already 0. We know that, right? So we somehow pick J equal to, because it's 6 about 5th, right? 5th. Do you agree with me? So this is pretty random, right? Pretty general enough. So under this assumption, let's do it. Then, what is the LK link? First of all, vertex K. Vertex K is what? Vertex K is this position, right? This position is like 2 over 5, and then 2 over 4 is the vertex position, right? This is the vertex position. And linked list is 6, 7, 11, 10, 5, 1, 2, right? So this is the linked vertex index information, right? Then we will form triangles. First triangle, like 6, 11, 7 triangle. And then we check whether K and J are the same, right? And then K and J are not the same. We already checked it. And then now, J is inside this triangle or not. But as I mentioned, this is too abstract. So now let's be specific. J is either first and second numbers in the linked list, right? Is just J the first number in the linked list, or is J is the second number in the linked list? So we should check this. Do you follow me? Not, right? Then integral val 1 is 0 because of this reason. So we did the val 1. Now val 2 calculation. Val 2 has 6, 11, 10 triangle, right? Already we checked this. So it is already checked. So we check whether J is either 11 or 10, right? 11 or 10. It's not, right? So val 2 is 0. Val 2 is 0. Of course, computer does this calculation. You program, and computer does this calculation. The third one, 10, 5, 6, right? So is J 10 or 5? It's not 10, but it's 5. So we had a hit, right? We have a hit. But with our ordering system, it's like this. So I will go upstairs and then analyze this thing with you. But before really deeply analyzing these things, I will go to the next triangle. So like take a look. Val of 2 is, val of 3 is non-zero, right? Non-zero, some integral, right? Some integral. And then down the next triangle, 6, 5, and then 1, right? This is the next triangle. And now we have a hit, another hit. We have another hit, either 5 or 1, right? 5 or 1, and then we have another hit, right? We had hit and hit. Then we should return non-zero, val 4. So in this sense, there are, at best, 2 hits. At best, there are 2 possible hits, either hitting this way or hitting the other way. So I will pause, and then you may ask questions. Then now is the time. Because we have a hit, we should consider phi1, phi2 always. So let's analyze this force value first. Force value first. Triangle 4, right? This is the triangle 4. And then this is the center, what center? 6, 5, and then 1. This is the fourth triangle. Under this assumption, I said this. Always, this is the first vertex of the triangle, right? And this is the second vertex of the triangle. And this is the third vertex of the triangle. And then, if it has 1 here, 0, 0, then it's called phi 1. Do you follow me? If it had 1 here, 0, 0, then it is called phi 2. And then phi 3. So, in this case, we can directly apply this formula. We can directly apply this formula. Why? Because as you can see, let's go to the definition part. Vertex, right? Vertex. And then we can form a triangle with faces. And then this I1 can be changed to 2 and then 3, right? So phi 1, x1, y1 is 1 and others are 0. And then phi 2, x2, y2 is 1 and others are 0. And then phi 3, x3, y3 is 1 and others are 0, right? So this is the first triangle, second phi function, third phi function. Depending on positions, we have different 1 location. So in this case, first triangle has, first vertex is the center of this phi1 function, right? This phi1 function. And then second vertex is the center of this second vertex function. Then we can apply this. We can apply this theorem. We can apply this theorem, right? First, second vertex formula. So by applying this formula, we return the value of this calculation. Why? We now have all the xy information, right? We now have all the point information. And this point information, and then this calculation will return some value by doing this. Now the next one. Assume that we consider the third triangle. So we return back to the third triangle. So this is the third triangle that we got. It's like this. Sixth position here. And then upstairs is 10th position, I guess. 10th position and then 10th position and then 5th position. Then by our orientation, this is the phi1 center, right? This is our phi2 center, and this is our phi3 center. Do you follow me? In this sense, our vertices are in wrong order. Why? Because we have phi1 value and then phi3 value. We don't have this formula, so the best thing is switching the role. In other words, we call this vertex 1, right? We call this vertex 2, vertex of the triangle 2, right? Vertex of the triangle 2, and then vertex of triangle 3. We initially called this, but we cannot apply this formula because our formula is for 1, 2, not 1, 3. So what should we do? We switch the contents of these two and then apply the formula. That's it. Then we get the result for this interval. So we essentially determine the integral of two functions using this. Yes?
Okay, so then you
sum v, value 1, value 2, value 3, value 6, and then return this as the AKJ. So after doing this, we will get, after doing this, we will get val 4, right? Val 4 is, for instance, like 0.1, right? 1, 1, right? And then after doing this, val 3 is 0.09, right? And then others cannot have any meaningful number. So later we store AKJ, or more precisely, A65 equals the sum of val, right? The sum of val, right? Sum of val. J is misleading, right? So sum of val, then it is 0 plus 0 plus 0.09 plus 0.11 plus 0 plus 0, right? Val 1, val 2, val 4, val 3, val 5, val 6, right? So these values are returned, and eventually this will store 0.2. Of course, mostly these values are negative because, as you can see, the slope of this and slope of this are multiplied, then they are opposite. So slope multiplication. So in fact, my assumption is not accurate. So you should say minus this one, right? So we should return minus of this one, right? And then minus of this one, and then 9. So our val 6.5 will become 0. Take a look. We have one slope, and we have the other slope multiplied together. Then slope-wise, this positive slope, negative slope multiplied negative. If k and j are the same, then we have the same positive slope multiplied positive slope, or negative slope multiplied negative slope. Then we have always positive. But when you have one off, then always there. Yes, they will take care of sign. So we don't have to worry about it. I'm just giving you an example. So please browse the idea part and ask. In other words, we are going from design part to the very, very specific part to really overcome difficulties. But as I mentioned, once you master these things, in the future, when you really apply this method to analyze some kind of shape. Then you break up, and then you determine nodes, and then essentially do the same thing, but your linked list might be a little bit longer. We allow 6 surrounding neighborhood triangles, right? But we may have more than 6 neighboring, maybe maximum 12 triangles. Or not. I don't think you will have 20 triangles, because if you have 20 triangles surrounding the given vertex, the shape will look like this. Assume that you have 20 triangles, and the shape will look like this. But this is not a good design, right? Once you design, the regular shape is the best, right? 60 degrees, 60 degrees, 60 degrees is the best. Then if you allow 60 degrees, then 60 degrees times 6 is 360 degrees. So this is a bad design. In other words, you don't have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 surrounding triangles. You don't have. In most cases, when you design nice, you have like 6 to 8 triangles or less. Right? Less isn't necessarily great. So around 6 is the best. In other words, assume that you are analyzing your design of, for instance, some shape. Then you break this up. You should break this up using fixed size triangles like this, right? Then after breaking up triangles, you should determine the indexing, right? Indexing for the first node, second. So you could determine, for instance, for 11th node here, 12th node here, 13th node here, and 14th, and any way you want, right? And then afterwards, you should make a linked list. For instance, 11th linked list should have, for instance, from the horizontal line, we go up, right? We usually start at the horizontal line and then find the surrounding node. Then this node, right? This node was not even labeled, so let's label them first. 15th node, 16th node, 17th node, 18th, and then 19th. Then with this, from the horizontal, we go up and then find the node, and then it is 15th node, and then 16th node, and then following it, right? So you do the same thing, but now the shape is not regular. We may have, but at least once you program well, then the idea is exactly the same. Only difference might be the length of this matrix. Length of this matrix is, or vector could be longer. Instead of just 6, you may allow like 20 or even 40. But as I mentioned before, if you have 40 surrounding triangles, then the design is very bad, right? It's like this. This kind of design isn't great. But as you can see, it's not very easy to make. Even how many triangles did I use? About less than like 20. Even this design is extremely bad. You don't have to design this. You should use small regular triangle types all over the places to cover the whole domain. So the whole domain should be covered by small triangles, right? And then we solve this using FE. And after doing this, you solve this the same way, and then form a surface. That surface could be your product, right? Or thesis. Yes?
So in this example that we just talked about, we had 30 total node points and 12
Interior node points, right?
So then we have this system, A times C equals B, and we need to solve
12 by 12 system. 12 by 12.
the dimensions of the system.
12 by 12.
So it's A is 12 by 12.
Right. Multiply by C.
Right.
That means 1 by, 12 by 1 column vector, right? Equals the right hand side, 12 by 1 column vector. B is not a matrix. It's a column vector. But we can consider vector as a matrix. Then 12 by 1 column vector. Let's take a break and then resume at, by this clock, 3. assume that you are asked to solve like problems like this. In other words, you want to analyze the, for instance, temperature at each point, right? That means you want to analyze this kind of shape using finite element method. Then you have vertices, right? So let's number the vertices. First one, this non-boundary first one, right? First one, second one, third one, fourth one, fifth. Any order you can number these things. Then you have the linked list, right? So like first one, and then this could be the second, third one. So linked list is third one, and then, third one, second one, and then going all the way like 1001, 1000, second one, and then this kind of things, right? Second one, third. So we can form a linked list like this. Then you can apply the same thing. In other words, once you program this thing, that kind of program can be applied for any shape. The only thing that did not match my case was irregularity. We used a regular rectangular case, right? So our automation generation worked fine. But assume that the shape changes. Then our vertex indexing scheme changed, right? First, second, third, fourth, fifth, and so on. And then we number these things. And then we create the linked list, right? Linked list. And then after doing this, we use the same program to solve. And then temperature will be represented by height, right? So each height represents temperature of this shape. Then you may analyze it. And then you think, oh, this has high temperature and it may melt around here. Then you may do other things to change the resilience, things like this, right? So these kind of things are, in fact, used in many areas. And as I mentioned, I am not an expert in automation generation. There are some dedicated computer scientists doing these things. In other words, they completely discretize the given domain with nice triangles. But as you can see, almost all triangles look very irregular, right? Look very irregular. That's amazing. Ours is a little tweaked, right? It's not great. It's good for automation generation, but it's not good for really solving the problems. So then, as you can see, the height is 1 here and then 0. Height is 1 here, height is 0 here. So my program doesn't provide the automation generation part, but at least once you create the vertex information and link information, then you can apply the same program to solve the problem. But others have way more efficient method to really solve the problem. And they sometimes do not rebuild the part, and they just found their company and then sell the product. They don't rebuild the secret. So because of this reason, there is no textbook implementation scheme. This book has this method, the other book has the other. Some books do not even have anything. They just explain theory like integral symbols, and that's it. You should do everything on your own. But at least you have one, after doing this binary, at least you have one routine that you can apply to write theses or to really analyze the temperature of the shape and so on. So how many vertices will be inside? At least roughly about 400 to 600 vertices could be inside, right? And then boundaries are like over 300, maybe more, yeah, over 300. So total like 1,000 vertices. And then linked list may contain for each. How many linked vertices? First one, second, third, right? 1, 2, 3, 4, 5, 6, 7, about 7, right? So about 6 to 8 is appropriate. But essentially assume that all these are correctly indexed and then linked list is given. Then what should you do? You don't have to do anything, just apply the thing that you have and then solve the problem. Then you will have temperature in height form or color form like this. It's up to you to choose color or height. If you use height, then you should represent these things in 3 dimensions. Then you see where the heat may affect mostly, or where the heat does not even affect at all. Then you can use expensive material or heat resilient material in this place, and you may use like cheap material. So this is a very important method in both math and computer science and mechanical engineering too. Especially, we cannot make airplanes every time. We should simulate. Then to do simulation, we should do this kind of analysis. So, for instance, assume that red represents the high temperature, then the material here should be expensive, and others could be cheap, could be very cheap here.
I noticed that's a non-simply connected region.
It's tougher, right? It's tougher, so we.
Will our method still work?
Yeah.
Just automatically?
Yeah. So once we have one method, we can apply. But the difference is this. If we are handling the Dirichlet problem, meaning just nice boundary and all the boundary information is given by functions. But in real situation, we may have mixed situation or like a Neumann problem. Instead of actual function value, we may have derivatives at some point. So in real world, we may have harder things involved, right? Then it's tougher to program. Our case is just a Dirichlet problem, meaning at this boundary we know the height at least, or we know the temperature at this boundary. Although this assumption you can apply the same thing. But if we change the assumption, then it's very different. But as you can see, when you have this kind of sharp place, we need more triangles. When you have this kind of flat area, we have bigger triangle. So in the past, I even assigned the homework, and then some student submit this kind of thing, as I showed you before. But as you can see, I don't like this kind of triangle. We should break up better to have a regular triangle type stuff here instead of this kind of sharp triangle. Then we do the heat analysis, right? Assume that air resistance, increase the temperature at surfaces. Then if we do the analysis, then we can sketch the temperature using heights. Then we know what place may have the heat problem. For instance, you are creating like a space shuttle or something. Then you should check these kinds well, right? So using finite element, we can simulate instead of really making 100 different shuttles. But let's return back to EG consideration part. So, as I mentioned, my program, my design is general enough to cover almost all cases like this. The only change is L vector, L sub k contained in our case exactly 6 surrounding nodes. But in general, there is no guarantee we have just 6. We may have 8 or 10. So we may have a relaxed condition on this. Instead of just using, for instance, 1,000 by 6, we may use 1,000 by, like, what would be relaxed condition? About 12 might be optimal, or 8 might be optimal, right? But to avoid any malfunction, it's better to make it big enough. And if there is no linked list after, for instance, 5, 6, 9, 8, 9, 11, and then there is nothing, then you can just fill the remaining part with 0. I'm assuming that you might be involved in finite element method programming in the future for your thesis or work, then you might change this. But they might buy commercial products because our thing is theoretical and very slow. Commercial product is written in C language, fast C language, or even assembly. They are way faster than our MATLAB style slow interpreter language. In any case, I explained the necessary parts, and if you have a question, ask. If you don't, then I will mention about the method of determining the matrix A and then the right-hand side column vector. Because we now formed lowercase a matrix, but now I will extend these things to cover the boundaries. And then by using these boundary things, we can create the right-hand side of the matrix, the system. And then by solving the system, we can find the C values. And by linear combination, we can solve the problem. Then now extension of kj, right? I used kj order. I vary k from 1 through 81, and then k from 1 through 81, assuming that 10 by 10 is used, right? 10 subinterval by 10 subinterval is used. But now assume that k is still interior, but j is not interior anymore. J is boundary. Then what should we do? In other words, k is still there, but j is now every possible node, not just nice nodes, interior nodes, but what if j is boundary? Then should we recreate the program? No. We can just recycle the code. How? In our checking, we did this thing by triangle, right? So first triangle, and then second triangle, and so on, right? So we did these things by considering individual surrounding triangle of k, right? Surrounding triangle of k, we did it. There is no reason to forbid these things for general k. In other words, assume that k is not just from 1 through 81. K could be 82, 83, 84, or 100, right? K could be anything. Then what should we do? So that's the next step we will do. Then essentially, we can recycle the same thing. We did this thing for k running from 1 through 81, but we don't limit this k number. We just allow any number. We allow any number. Then what is the difference? In the past, we had 6 triangles, 6 surrounding triangles. But assume that we are here, then this k may have less number of triangles, right? That's the only difference. That's the only difference. So we can allow k to be anything. In other words, you don't change any program part to extend this j value from 1 to 121, right? J value. So you don't really change anything. Just allow. Then that's done, right? So we now have matrix A initially with 81 row by 81 column, right? We initially had it, but now we do not limit k to 1 through 100, 1 to 81. We allow it from 1 through 121, right? We allow this. This is a little bit misleading. So I will just write the difference value. I write difference value. Right? So we can run the same program for the whole thing. Then as you saw, when I designed the linked information, I used 0. But there is no 0 node, right? There is no 0 node because I didn't use 0 index for actual node. In other words, when you check conditions, it doesn't hit these 3 conditions. I said this, j equals k, right? Or j belongs to linked list of k, and then else return 0, right? So take a look. I don't change anything to extend this program to run for 1 through 121. So let's look at let's really follow it. Now, k is not just 1 through 81. K could be like 85. Then he came here. Is it possible? Is this possible or not? It's not possible, right? Then is this possible? It's not possible, right? It's not possible. Oh, it's possible, right? It's possible. Then it runs the routine, right? It's possible. Then it runs the routine. And then if these do not happen, in other words, node number is 0. There is nothing. Node number is 0, then nothing. Then what happens? It runs and then.
Why doesn't J go that 121
J goes from 1 through 100. You mean K, right? So I used so J is right. J is used here. Yeah, the reason is symmetry. Symmetry. Right, right. Symmetry. In other words, when you really program, K runs from 1 through 81, right? And then J runs from K through 121. Do you follow me? Why? Because of symmetry. Once we know the half, then we can know the remaining half.
J always runs from 1 to 121.
Because of symmetry. Take a look at the symmetry. Yeah. Then because of symmetry, we don't really have to run 1, 1, 2, 2. 1, 1 is necessary, but for instance, we don't need K equal to 2, J equal to 1. We don't need. So from this first, when K is equal to 1, we calculate, when K is equal to 1, we calculate it from 1 through 121, right? That means we have A11, A12, A13, and then all the way up to A1, 121, right? We have these things. Then, now we go to K equal to 2. Then we do need K A21, because A21 is the same as this, right? Because of the definition they are same. So we don't need this. So to save our memory or time, we just do this. So we just do these things, and then after doing these calculations, we copy this way. We copy this way. A Kj equals a Jk for the remaining part, right? For the remaining part. And then we create appropriate indexing, right? So we do the appropriate indexing.
So in the end, we should have a 121 by 121.
No, what? Because in real situation, all we need is the 1 through 81 numbers in this position, right? And then you may have extended area here, right? So all we need is this part. But this part is stored for B calculation. So in the real situation, 81 by 121 is less. Of course, you can make a matrix big enough to have 121 by 121, but there is no usage of anything over 81 in this row. Because we are forming, eventually we are forming A, C equals B linear system. Then A consists of 81 by 81, and then C consists of 81 by 1, and then B consists of 81 by 1 numbers, right? We eventually form this thing. So assume that we created 121 rows. Where do we use those lower portion? So we don't even consider, just we go. But why do we need the right-hand side? Because the A value on the right-hand side here will be used this portion will be used to calculate B. This right-hand side itself is not necessary in forming this system. In forming this system, A can be just created by considering 1 through 81. But then how can you calculate B? Because B consists of these combinations. So we create this thing and then use this thing to determine B and use this square matrix to form A and then solve this system for C. Any questions up to this point? Then now, how do we calculate B? It's very straightforward. B calculation is very straightforward. As you can see here, B calculation comes from just this thing. Just this thing. Then as you can see, we don't have G, right? G is 0. Right? We have G equal to 0. And this is called AKJ, right? This part is called AKJ. So B is nothing but sum of CK multiplied by AKJ and then summing it from L plus 1 through capital N, right? 82 to 121. I will write down these things in simpler form. This is a theoretical form, and in simpler form, Bj equals minus Ck and then Akj and then K running from L plus 1 through capital N. Like this capital N has nothing to do with our M and N, but that's theoretical boundary. So now we stored AKJ on the right-hand side, right? AKJ that is required here is stored. AKJ is stored right here, right? AKJ is stored right here. Any questions?
We still know the C.
No, we know the C at the boundaries. These are all boundaries. K boundary C is known. Right? For instance, what is the boundary? What is the height? Then use the boundary condition. What is height here? Then use the boundary condition. We all know the boundary. So we now know the B. But in actual calculation, take a look. Because A, J, K, and AKJ are the same, right? So assume that you need a 101 value. Then, oh, we stop at 81. Then should you worry? Or what should you do? What should you do? If you need A, then A 1/800 can be used, right? 1 and 1/8, this one. So if you need A 100.1 in this calculation, then instead of using A 101, you can use A 100. That is stored. Use the symmetry. Use the symmetry. So all these values are stored on the right-hand side, and then you can just add these things and then take just simple. I showed you like three-line portion of the program, and then you determine Bj, and then you loop for J running from 1st through 81, right? J running from 1 through 81. For each J, we calculate this thing. So B1 is calculated with 1 here, right? And then B2 is calculated with 2. Once you see 101, then it means 1 in this one, and then you do this. So in your program, you may make this kind of thing, and then calculate B. So now, what do we have? We have this matrix A, and then now we have B matrix, right? Then now it's time to form uppercase A. Uppercase A is nothing but the matrix A from 1 through L, and then 1 through, I do not know MATLAB code, but roughly this is the collection of, right? We are limiting our matrix to 81 by 81 matrix, right? This way, then all we need to do is solve Ax equals B, and then x is determined. And then once x is determined, then we now have x, and then C value from L plus 1, and then C value of n to form full coefficient set. Then this full coefficient set combined with basis function solves the problem. So these are the steps, and I showed you the code before, and then you can remember these things. But knowing this theoretically is more important because, as you know, this kind of routine is not very difficult to implement. And what else? This kind of thing is not very difficult to implement. So essentially, once you understand, nothing here is very important, difficult. So let's finalize this part and then go to other part of the review. So we have a domain. Then we discretize the domain using nice triangles like these, right? We discretize the domain like this, or assume that we are solving this kind of temperature problem of the Earth, right? Of the Earth. Then we form these kind of small triangles, and then we solve certain Navier-Stokes equation problem, and we solve the temperature problem of the sea, and then we present the temperature in heights or colors. Then we see the sea level temperature is cold here, it's hot here, and so on. And then how to avoid this kind of problem, such as El Nino or La Nina or something like that, then we can do some kind of act. In other words, let's send the ice tanker and then dump ice here or something. And a few more things that I want to explain is the way of creating finite element. We used triangular finite element, right? But this isn't the only finite element. You can create rectangular finite element, right? Or you can use polygon style or tweaked thing. And we used simple node points, but it's possible to allow the nodes in between, right? These kind of things are also considered. But why didn't I cover these things? Because if we allow these kind of things, the involved basis function isn't straightforward anymore, straight edges anymore. We have many curved edges. So it's possible to consider other shapes like these. But most popular one is the one that I explained. And you can create faster algorithm with simple triangles. So let's do it in abstract form. Discretize the domain, right? First thing is discretize the domain. And the second step is solve this, right? Instead of the given differential equation, right? So this is Galerkin's approach. Instead of solving the differential equation, solve this by solving linear system ax equals b, and a and b, you already know the meaning. Then, after this, assemble the solution. Assemble the solution by just doing C that we found with this one is boundary, and then basis function. No matter what domain is given, once you know the node information and link to vertex information, you can form a basis function, right? You can form basis functions all over the places. Then with this known basis function, we determine the CK by solving this thing, we do it. But here, in discretization, vertex and linked list thing is the one that is tough. In automation, that part is implemented many different ways. For instance, someone gives you a shape. Your program should create the vertex and linked information. Then how can you do it? This kind of thing is, in some sense, research area, right? Not just the triangular shape. Tetrahedron shape is used for three-dimensional shapes. And how to determine this kind of tetrahedra all over the place. That kind of thing is the major area of research. Still, people develop things and publish papers or make them secret and then make companies and then sell products. So after doing, solve this thing, and then determine C, and then with this determine the basis functions we can form, and then either represent these things using heights or colors. Then with this you analyze, for instance, C temperature or your part temperature after some kind of like test, then simulation, then you know the temperature at each point by just doing something similar to this thing. Oh, do you know the temperature of this part? Ij represents the part, right? This part at this point, then you can say, oh, it's possible because we already know we can do these things with the CK, right? So after doing this, we can combine these things with CK. Then we can know the temperature, right? So we can show the temperature of every place, and then we can investigate the critical part, and then we use expensive material for this kind of part. Roughly, FEM is completely summarized and reviewed. But if you still have a question, you ask me. If you don't, then I will review for the whole course for other things. It is, my code is very inefficient, but some people develop faster link finding code. So mine is this. For instance, vertex is determined, right? So vertex K gives us link K. How did I do it? I did it this way. Once K is plugged in, then we know the vertex, right? So vertex becomes the center, right? Vertex becomes the center. Then I investigated 6 points. Center plus east side, right? Center plus east side, meaning about 1 over m is added. Then this is a number, right? This is a number, for instance, 0.6, 0.5, right? This is number. Then I find the vertex function. Find the vertex function, right? Find the vertex function with this kind of input, right? Then it goes in, then it checks individual vertices, and then find the matching vertex, and then send the index of that vertex, right? Return the index of the vertex, right? For instance, if we plug in 0.6 and 0.5, then it is the vertex number like 42 or 40, then that number is returned. So I made this kind of. But direct comparison wasn't good. Direct comparison was not great because when I say 0.6 and then 0.5 is equal to, for instance, vertex of 42. If I say this, even though this vertex is in fact 0.5 and 0.6 and 0.5, sometimes it couldn't check it. So I felt very strange. So instead of using direct comparison, I used the norm concept, right? If the norm of 0.6, 0.5 minus vertex of 42 is small enough. How did I determine small enough? I just used this kind of number, but you may find better number, right? In other words, it's less than the 1 over m or n, right? The subinterval value, right? It's less than subinterval length. Then return 42. I intentionally use numbers, right? But all these are letters, right? Indices I, J, and then vertex number K or something, right? All the things are described with explicit numbers. So this is my intention. I wanted to do it, but this didn't work, right? So I changed it to this form. You're right. So I did this thing for each position, right? Least position or so. I store the returned value at, for instance, link number, right? One position has 42, right? And then answer, right? It's not very appropriate. Maybe 41 has this kind of thing, right? So once we have vertex position, we have linked vertex vector, right? For a matrix. Any other questions? Then, because we do not have enough time, let's look at our summary notes and then browse what we studied in this course. First of all, bit numbers. Once we have a number, it's in our head, but how can we represent the number using computer? We use binary, but it's not just for binary. We can use any base, right? Any base can be used to represent any number. So this is the conversion used, especially when you use binary, then we have this kind of. And I mentioned these things before, but we can use just binary representation to represent plus number, minus number, fractions. How? We used this kind of design, and then we store this fraction bit information like this, and then we store this exponent information like this, and then we use sign information, and then we form numbers. So once we have this kind of thing, it means a number. And we completely covered these things. You even programmed these things. And then afterwards, we learned about numerical technique. Of course, this is the intersecting area of both numerical analysis course and this course. And then we wanted to find the solution. Then using Newton's idea, we did it, or iteration, we did it. And then Newton's idea, instead of using this form, we can use this kind of difference, because what is the difference between the derivative and this one? Almost similar other than the representation. And using these things, we developed a method such as Euler's method, and then we did the integral using just addition, right? Addition at some point, right? Calculate the values at some point and add these things. And the derivatives are also defined by doing this finite difference, right? We created read and then consider subtract the differences and then divide by the grid length h. And then we learn about the solving A x equals B type system, right? A equals, and then we can solve this kind of system using direct method like LU decomposition or Gauss elimination, or we can solve it by QR decomposition. But better idea is, because of the slow performance, better idea is using iteration. But this also has drawback. The drawback is, even though the problem is simple in LU decomposition or others, it could be complicated in this iteration because it may not converge. So we covered the method of Gauss-Seidel and successive over relaxation, and we even handle nonlinear system. F of x equals 0, and then f of x looks like this, and then g of x looks like this. And we can even solve this thing using the Hobian that I mentioned, and so on. And then after solving system or equations, we want to interpolate the function. For instance, how can we store the music information without storing too many numbers? We don't want to use too many numbers. So how can we store data without storing too many numbers? The idea is using necessary information, necessary pieces of information, such as coefficient of a polynomial, or coefficient in front of sine or cosine function, instead of storing the detailed numbers representing music or something. This kind of thing is from interpolation, and we do the interpolation by using many different methods. Assume that we have like n plus 1 point information, then you can find the polynomial, exact polynomial, and then this kind of exact polynomial can be determined by Newton's divided or Lagrange or other things. I limited stuffs to nice cases called spline. When you have spline, instead of oscillating style function, we can use nice, smooth stuffs to represent. So spline is very useful, and ready-made spline is called B-spline, right? Already made spline can be used. Just assemble these splines by linear combination, then we can form the actual spline. So this kind of thing is covered in the course. And then we can represent the function using this multiplied by ak. What is the advantage of using this thing? Then we don't have to store this function information because function is already there. So we only store this ak. Then we can save space. This is called Fourier transform, especially finite Fourier transform. And another method is least squares method, right? We have least squares. Assume that we want to represent the gathered information using line or curve. Then we can determine the order of the curve and then determine these coefficients. So how to determine is explained here. So all these cases were done. So roughly this is it for the approximation or numerical method, and afterwards I briefly covered FFT, but because it was also covered in numerical method, I don't want to return to that part. And let's consider ODE. We are solving differential equations. Then we do this thing. We break up the given domain using usually evenly divided subuniverse. And from x input, we want to determine x input and y input. We want to determine x out and y out. Right? We want to determine this thing. Then how can you determine this thing? We usually determine x out very easy by just adding h, right? We add h to determine x out. Then how can you determine y out? Y out can be determined from y in plus some number, right? This number determination, k, varies. Euler developed one idea, and Hoyne developed another idea, right? And Rangapakara developed another idea. So they developed many different ideas, and we learned the idea of this k determination. Sometimes just one number is used, sometimes average of two numbers is used, or average of four numbers, weighted average 4 numbers is used. These kind of things can be used. So these are the essence of the method. And assume that we have a system. Then instead of just considering x in, y in, we can consider x in, y in, and z in, right? X in, y in, z in. Then you get x out, y out, and then z out, right? So we add one more line like this and then do the calculation. And then we can use same idea, right? We can just add k like Euler, or add k and then some combination 4 in RK4. Then the next question is this. Assume that we have higher order differential equation instead of just first order. What if we have higher order equation? We assume that we have this kind of equation. Then how can you solve the equation in numerical method? Then it's tough, right? So we should introduce this kind of idea. Y becomes new variable, and then z becomes some new variable, right? I mean, it's a little bit vague. Z is not good. We should say y prime, right? Then with this assignment, we can form a system. So it's like this. Kth order, one-dimensional equation, right? One-dimensional equation becomes first order k-dimensional system. So this is the idea, right? So kth order one-dimensional becomes first order k-dimensional. With this, first order can be solved by the method. So we covered all these things, and then all these are initial value problems. We'll assume that we have initial condition. When time is equal to 0 or time is time 0, then we can solve these things. But what if we have boundary value problem? In other words, we have the value at 0 and we have value at some time, but we don't have second derivative conditions or something. Then we can use like shooting method or finite difference method or collocation method or finite element method. So let's briefly review them. Finite difference will be returned later, so I will mention about two other things. Shooting method depends on the idea of guessing this. We don't have this value, but we guess this value. So we use, for instance, alpha 1, and if this value is 2, this value results in higher value in the end, then we lower this value, and then we get lower value, then we pick this guess in between, right? Higher value and lower value, and we guess this using bisection idea. So this is shooting method. And collocation method is this. Collocation method is guessing the solution using this kind of function, especially we use polynomial here, or trig functions here, or exponential with complex number. So we determine ck by equating these things at usually equally divided points, right? We determine this ck by using this point, and then equally divided points, right? Equally divided points. We equate the values, right? We equate the values at these points. Then we form a system, and we solve a system to determine the ck. So superficially, this looks similar to finite method. This looks similar to finite element, but function, basis function, and method-wise, they are very different. This is collocation. The other one is finite element that we covered, right? We break up the interval and then solve the problem. One-dimensional, two-dimensional, even three. Three-dimensional case can be also programmed similarly, but that requires like at least 1 month of lectures plus. So I don't want to go into three-dimensional domain. Domain is three-dimensional. So we covered one-dimensional domain or two-dimensional domains, but we didn't cover three-dimensional domain. Then how can you represent the result? You only raise color, right? Red means hot, like blue means cold. Then, as I mentioned, finite difference. Finite difference is a nice method. But problem is this. Sometimes we cannot apply finite element method to solve cases, especially when you have some steep problem. It's very difficult to use finite difference method. So it's like this. If it gives you the nice result, finite differences is the easiest one you can pick, right? It's the first one you should pick. But if it doesn't work, then you can consider shooting or collocation, right? Or finite element. So it is the first method of your choice. It should be the first method of your choice. If it doesn't work, then you may consider other things. Then what is the idea? Idea is very simple. We have differential equation like this, right? Or something t, if you use time variable. Then this form is not easy to handle because of derivatives. Because without certain techniques, we don't know how to solve this kind of problem, generally. So instead of worrying about derivatives, we just remove derivatives. So initially this is global, or at least inside the domain, right? Global inside the given domain, right? This holds for every point in the domain. But instead of worrying about the whole domain, I will magnify this thing, and then, so domain is magnified this way. And instead of worrying about this whole domain, we break up the domain into small pieces, and then we consider the difference at each, the representative of these things inside this. Then we have yn plus 1 minus yn over h to represent replace over h to replace y prime, right? So y prime locally can be replaced by this simple terms, right? Or y second derivative can be replaced by right? So we can replace these kind of complicated derivatives by just simple terms like this. Then eventually we will have equations of system of y1 through yn generally, right? For this we use this, for this we use next one, for this we use next one, and so on. So we form this kind of small simple equations and solve this kind of equation. This is the idea. And same idea applies for any dimension. So we now apply this kind of idea for partial derivatives. Assume that you have u function of time, x variable, and y variable, and z variable, right? Assume that you have this kind of thing. And then you are solving this kind of differential equation. ut equals uxx, uyy, uzz. Then inside a given domain, we break up the domain, right? Time-wise, for instance, we break up by 100 small time steps. X direction-wise, we break up by 100 small x direction steps, and then dy steps and dz steps. Then just we replace these things by like u of generally time, right? So k, and then these were used with indices like this. I, J, L. Not a good idea. So this kind of, right? I represent x, J represent y, and so on. And then this derivative makes this thing like this, k plus 1. K plus 1, and then k, I, j, k. So this is not actually a function. It's just array, right? Array. It's an array. And then using arrays, differences. So what is the difference? This here, u is, I will let you know the difference. Here, u is a function. Here u is a function. Here, u is a variable or unknown, right? So you should know the difference, right? We have a function upstairs, but now we have variable or unknown. It means we have many unknowns, right? This is one unknown. This is another unknown, right? We have many, many unknowns, right? We have many, many unknowns. Then we should determine unknowns using some kind of solving technique, right? Some kind of solving technique. How? So depending on method, we can create the stencil. In this case, it's very difficult to create a stencil in three-dimensional space, right? So even this is not enough. We need one more axis, but we don't have more axis. So just vaguely add stuff. Then it is time direction, right? So time direction, we know this value at this time, but we don't know this value, right? And then we know this value in x direction, right? And then we know this value in x direction, we know this value in x direction, and we know this value in y direction, y direction, y direction, and then z direction, and then z direction. So it's not accurate, and it doesn't have any meaning, but at least we can use these kind of values to determine this step. Then how can you determine this kind of value? Usually using boundary condition or initial condition, we determine these known values. So using these known values, we determine the unknown value. So there are many, many unknown values. Then we determine these many unknown values using certain approach. So depending on problems, we should determine unknown values differently. Especially when you have elliptic equation, such as the Laplace equation or Poisson equation, we cannot determine this value using these things. It's not possible. We cannot determine this way. We cannot do it. Why? Because we don't know this value in the first step. So this approach doesn't work. Then what should we do? We should allow this kind of thing. Usually, elliptic equation has all the boundary values known, right? So all these are known, right? These are all known. And interior is unknown, right? These are all known, but interior is unknown. So what you do is this. Oh, we assume these values. We assume these values. How? We usually use line connecting these two poles, right? This may have height here. This may have height here. Then we connect them, then we can determine intermediate heights. So we use intermediate heights to fill these things. Then we at least have rough height information at each node, right? After doing this, we create this kind of stencil. U xx plus u y equals 0 gives us what? U I plus 1 j minus u I j plus u I minus 1 j in x direction, right? This is the derivative in the x direction, and the derivative y direction can be written similarly, right? Then we can solve this for uij. Then uij equals something like this. Oh, it is 1/4, assuming that delta x and delta y are the same. Assuming that delta x and delta y are the same, then 1/4 ui plus 1 j, ui minus 1 j, and then ui j plus 1, and then ui j minus 1, and then this f might be added, right? f I j, whatever it means, right? Then this is the idea behind the calculation. So usually Fij is not is exactly at this f value, but some kind of delta x squared multiplied with 1/4 and something like that. But I just use something. So then if we create a stencil, it looks like this. We know to determine this unknown, ij's position, we use I plus 1, right? I plus 1 j position, or I minus 1 j position, right? And then ij plus 1 position, and then ij minus 1 position. To determine this thing, we should use these 4 surrounding points, right? It's like diamond shape. We use these known values to determine this unknown value. So we fill these things, then we determine this value by going through these surrounding points, right? And then we determine this value by going through these surrounding values. We determine this value by going through. Going through means by applying this formula, right? We go through this way. And after going all the way, we determine this value using surrounding, and then we go all the way up. After going up, once one cycle is not good enough, then we return back, do the next cycle, right? And then return back, and then we better the results. And then we eventually stop when the difference between the previous result and the current result isn't big. So this is the elliptic case. And then another difficult case is wave equation. Wave equation looks like this. Wave equation looks like this. And for general step, it's not very difficult. For general step, it's not very difficult. So let's look at it. If we write it in usual finite difference steps, so u of tx is the order. So t in t order, right? Minus 2 times uij, and then ui minus 1j over delta t squared equals the similar thing with j. J plus 1 uij, and then ui j minus 1 with delta x squared. So this is the situation. Then we solve this equation for this thing. For this thing. For general steps, this works, but for the first step, we don't have the bottom value. For general steps, it's okay. So take a look. If we recycle the thing, then this point is represented here. This is the unknown point, and this point is 1 down, right? And then this point is 1 more down, right? And then this point is 1 right-hand side. Right? This point is right here. And then this point is right here. So we use these things to determine this point. When you have all the necessary points, then this works nice. But for the first step, we don't have this value. So first time step is crucial in wave equation. Some people blindly apply this thing and got strange result. First step is everything in some sense. So you should program first step. How do we do the first step? The idea is very simple. Idea is this. We do the first time step. So the thing that I explained is after first step. After first time step, the one that I gave you works. But for the first time step, we cannot use it. The same formula. For the first time step. What should we do then? For the first time step, we should revisit the left-hand side. The right-hand side is the same. But the left-hand side changes. How? UTT is the left-hand side. This should change. How? UTT generally is equal to h squared f of like I plus 1 minus, in one-dimensional case, I, and then fi minus 1. This is the general one-dimensional approach in time direction, right? In time direction. In general, but this doesn't work because we don't have minus 1 step of time, right? Because we don't have this, we cannot work. Then what should we do? We use this idea. Generally, finite difference AB means derivative of the point around A, right? Around A over 1 factorial. So this is approximately identical. Then what about the second derivative? Second derivative of A is approximately identical to ABC, right? So this is the idea. We are using this idea. So what you do is forming this kind of thing, and then, especially in the case with one less time step, we form 2 points. Time 0, and then time 1 step, right? Then what you do is this. F of time 0, and time 1 is approximately equal to f prime second derivative of time 0 over 2 factorial. So this is used for time 0 step. Then, time 1 step, then, so time 1 step might be better, but doesn't matter. So we are calculating this. So let's do it. By definition, this is f of time 1 times 0 minus f of time 0 times 0 over time 1 minus time 0, right? And usually this can be replaced by f primed of time 0, right? Primed of time 0. And this is nothing but time 1 minus time 0, f of t1 minus f of t0 over time 1 minus time 0. Right? So we replace the left-hand side by this thing. This is all you need to do. Then roughly, the left side looks like this. UTT is equal to, by multiplying these two 2 factorial multiplied by f, right? Something like this, right? Then if you use delta t to represent this thing, then delta t, and then delta t, and then u, next step, I plus 1 j, right? And then this one is ui. Do you follow me or not? Right? This is the time step, ui plus 1 j, and then this is the derivative, right? Derivative. So u usually derivative in the direction t, time direction. Right? Derivative of at some point. If you don't follow me, ask me. Then we can replace this time step by this thing. U I plus 1 j minus u j over delta t squared, right? And then this thing. So UTT should be replaced by this kind of thing. Then we can form the thing. We can multiply both sides by delta t, then delta t and the delta t squared multiply to delta t and so on. So we can form new, and then 2 is divided. And then these kind of things should be done to determine the next step. So roughly, we covered all the necessary cases. And I hope you can use these kind of techniques in your work or research or doing thesis or something in the future. And if you have still a question, you may ask me personally. And I wish you a nice vacation after this.